Parallel resonance circuit is otherwise called as the current at the resonant is minimum or tank circuit. At resonance, the power factor is being unity. So either in the series resonance or in the parallel resonance, both the cases, the power factor is unity. So always the reactive part of the impedance and the reactive part of the admittance must be 0. So we get the expression for the resonant frequency. At resonance admittance Y is minimum, impedance is maximum, current is minimum. So in the case of the series RLC circuit, parallel RLC circuit, R, L and C are parallel. This is a supply voltage and this is a current source. So admittance is Y is equal, represented as Y. It is the summation of here YR, YL, YC. So it is nothing but 1 by ZR, 1 by ZL, 1 by ZC. So it is nothing but this expression. Okay. In terms of J terms you are getting. Okay. So the reactive part. So this is the active part. This is the active part and J term after the imaginary part. This is called as a reactive part. Reactive part should be made 0. Okay, for the parallel resonance as well as for the series condition. Here we going to see that at resonance the reactive part is made as 0. Okay, after simplifying it we are getting the expression omega r is equal to 1 by root of LC. Okay, so here we are substituting, finding out FR is equal to omega r is nothing but 2 pi FR. So FR is equal to omega r by 2 pi. So substituting this omega r value, we are getting this thing. Okay, so FR is equal to 1 by 2 pi root of LC. So here in this parallel resonance circuit, Q is equal to IC by I is equal to IL by I. This is called as the resonance at, there is current at resonance minimum. So here the quality factor is IC by I, IL by I. So here it is R divided by omega RL is equal to omega R CR. Okay, so this is called as the current magnification. So second case if you are taking, here this R and L are in series with parallel with capacitance. Okay, here this Y is equal to admittance is equal to YL plus YC. Here it is YL as well as here we are having the resist, that is R is there. So here it is R plus J into XL plus 1 divided by minus J into XC. So we are writing the expression and finding out the value. Okay, at resonance, here this is the active part, reactive part we are making it as 0. So reactive part of the admittance is made 0. So when we are making it as 0, we are equating it and then finding out the value of the omega r. So omega r is equal to root of 1 by LC minus r square by L square. Okay, so reactive part alone we are taking it and equating it to 0. After simplifying we are getting the value of resonant frequency for this condition. Fr is equal to 1 by 2 pi root of 1 by LC minus R square by L square. At resonance, the admittance is denoted by YR. Okay, here this active part of Y. Okay, admittance is the active part. So YR is equal to the active part we are substituting and ZR is equal to 1 by y naught. So finding out this value, there is this value. So here we are finding out at resonance. Okay, ZR is equal to 1 by YR. Okay, YR, 1 by YR value we are getting this. It is nothing but ZR is equal to L by CR. Okay, next condition, case 3 is that what is in the case 3, here the inductance and resistance are series, and this is again parallel with resistance and capacitance. So similarly here we are finding out this. Here this L means represents this leg. There is R1 and L. Here YC means it is R2 and C. So we are having this R1 plus this, R2 minus this. So after simplifying the same way, we are equating here. This is the active part and this is the reactive part. J term is called as a reactive part. Reactive part we are making it to 0 for the resonance condition and finding the expression. So here simplifying we are getting it as omega r term. Okay, 1 by root of LC into root of R1 square minus L by C divided by R2 square minus L by C. If R1 is equal to R2, if both are equal, omega R or omega naught is equal to 1 by root of LC. Here when R1 is equal to R2, which is equal to L by C, so Z is equal to root of L by C.